Okay, so today we'll start with an announcement. Quiz 2 will be next Thursday, a week from tomorrow. Out at 3 p.m. just like last time. 24 hours to do it. Open book, open note, whatever. Just please don't talk to anybody. Okay. And also note that the week after that, so 2 weeks from now, we'll have our first midterm. Yeah. Which is consistent with the syllabus, I think. Just looking at it, it's consistent with the syllabus. Okay. So we started talking about partial derivatives yesterday. Sorry, Monday. And we left off saying that just like in calculus 1, we would like to iterate derivatives, take higher order derivatives, right? Second derivatives, third derivatives. Now, considering partial derivatives. So let's examine what happens here. Mechanically, it's just the same as what we would do in calculus 1, right? So start off. Why don't we let f of x comma y be equal to the polynomial x squared plus 5xy minus 4y squared. Let's first calculate the first partials. First partials. Partial f, partial x is what? 2x plus 5y. Good. Right? Differentiate this with respect to x. Differentiate this with respect to x. Y is a constant, right? So the constant 5y stays, and the derivative of x is 1. Differentiate this with respect to x. Well, there are no x's, so it's just a constant. It goes to 0. Now, how about the partial derivative of f with respect to y? Similar procedure, right? Now we're just considering y. Yeah.
5x minus 4y.
Yeah.
Minus 8y.
Yeah. Good. 5x minus 8y. Okay. Now, how about the second partial derivatives? That is to say, I may take this and differentiate with respect to x once again. So partial squared f over partial x squared is the derivative of this function with respect to x. Yeah. 2. Good. And partial squared f partial y squared is differentiating this function with respect to y. What do we get there? Yeah. Just -8. Good. But there's more we can do here, right? I may also differentiate partial f partial x with respect to y, right? So partial squared f over partial y partial x, or to help you remind you what order we do the differentiation in, we think of it like this, right? So we want to take the derivative with respect to y of this function. Yeah. So what does that give us? Yeah. Just 5, right? Now x is a constant, and we differentiate with respect to y. Similarly, I could take the second partial derivative of f first with respect to y, and then take the derivative of the first partial with respect to x. What does this result in? Yeah. That's okay. Were you gonna say 5 as well? Yeah, good. It's 5. Okay. So all these are second partials. These two and these two. And in particular, these two are called mixed partials. Okay. So this is nice. It turns out for this particular function, f of x comma y, it didn't matter if we differentiated with respect to x and then y, or with respect to y and then x, we got the same answer. That's not always going to be the case. But we can write down exact conditions under which it necessarily must be the case. Excuse me. Here's the theorem. So let's suppose f, the partial derivative with respect to x, the partial derivative with respect to y, and the mixed partial all exist. In an open ball around some point, x naught, y naught. And furthermore, we will also assume that the mixed partial f x y is continuous. At this point that we're considering, x naught, y naught. Well, if all this is true, then the other mixed partial, fyx, must exist. And what do we have? fxy evaluated at our point of consideration, x naught, y naught, is equal to fyx evaluated at x naught, y naught. This is known as Clairaut's theorem. By the French mathematician Clairaut. So I will almost never ask you to verify all these conditions. Just want you to see this and recognize that the fact of the matter is that most all functions that we deal with will satisfy these conditions. So if a function is given to you by some formula, you'll be able to tell right away, or you should most often assume that these conditions are met and that we can interchange the order in which we differentiate with respect to different variables. Okay. But just be aware that this isn't always the case. Now, it's pretty inconsequential if we're just considering examples like what we set f to be in the first case here. Let me present you a problem in which this theorem saves us a gigantic headache. So let's let h of variables r and s be equal to r times e to the 5s plus e to the r cosine of r plus the inverse tangent of r divided by the square root of 1 minus ln of r. Let me ask you to calculate partial squared h partial S, partial R. Okay. So as I've posed you the question, what should we differentiate with respect to first? Calculate this mixed partial. Yeah. Now, maybe I should clarify. If I didn't know Clairaut's theorem, what does this force us to differentiate with respect to first? R. Yeah. Which means we would have to differentiate this expression. Right? But notice that this complicated function has no s's in it. Right? So as far as s is concerned, this part of the function is just a constant. So we apply Clairaut's theorem, right? Okay, so what's the derivative of h with respect to s? We get well, like we were just saying, there's no s's in here. So this part of the sum goes to 0, right? So what's the derivative of r times e to the 5s with respect to s? Yeah. Yeah. 5r, 5s. Now if we take the mixed partial, what do we get? Differentiate this with respect to r. Yeah. Yeah, just 5e to the 5s. The derivative of r is 1, and everything else is a constant as far as r is concerned. Okay, so by switching the order of differentiation, we turn what is maybe like a 30-line calculation into a 1-line calculation. Now, point of this theorem for our purposes is that when you're asked to compute a mixed partial, you should carefully consider which order of differentiation will be easiest for you, and then just do it that way. Okay. Yes. Something that takes a lot of work to construct. So try to construct such a thing on your own, and then maybe we can talk about it in office hours or something. Yeah. For this concept, it's safe to assume that we can so well, this has this place where it's not defined, right? So clearly this formula doesn't apply where the function is not defined. So just be careful of that. But for by and large, yes, it's okay to assume that you can interchange those as long as you understand the basic behavior of the function that you start out with. Good.
Very similar. So we can assume that at the point range versus result.
Yeah. We won't say that you're allowed to use Clairaut's theorem most of the time. It's fairly safe. You'll be told when you can't. Is really more the thing. Good. All right. So all that being said, let's now talk about linear approximation. What is the purpose of writing a tangent line to a curve? Why do we do that? Yeah. Yeah, to get some notion of what the slope of the curve is at that point. There's also another implication of that. Here's a schematic diagram. Here's some function of one variable. It's the graph of it, like it's f of x. Here's some point. Here's a tangent line. I don't know what the formula of this graph is, but if I happen to know the derivative here, I can write a tangent line, and in a small neighborhood of that point, I can come up with a fairly decent approximation of the value of the function there by just evaluating on a line. Right? So this is one of the main uses of the tangent line, is that if we have a really computationally intensive formula for our function, or if maybe we just have some differential data about it and don't know what the formula is, near a given point, we can approximate the value of the function by just plugging in to a linear equation, which is much easier to compute than in the general function, right? So we want to imitate this construction in arbitrarily many dimensions. We want to come up with an affine linear function that approximates an arbitrary function near a point. By near a point, I'll mean in some open ball around a point on the graph. That's exactly what this is, right? These parentheses I put in here, some open interval around the point on the graph. So here's a proposition. Let's take a function f, which maps e into real numbers r, where we assume that e is a subset of Rn. And also, we'll assume that f is differentiable. At p, some vector in E. Okay. So if the magnitude of x hat minus p hat is close to 0, then we can say the following. The function value at x is approximately equal to the function evaluated at p plus the gradient of f evaluated at p. Sorry, hold on 1 second here. Dot the vector x hat minus p hat. Okay. So remember on Monday, we introduced this notion of the gradient, right? It's the vector of partial derivatives of f. So I told you that somehow this is a multidimensional analog of what we use the derivative as. We take that analogy, this expression looks almost exactly like the equation of a tangent line, right? F function evaluated at some point plus the derivative times x minus that point. But since the gradient is a vector, we now have the gradient dot x minus our point. Okay, so let's just write here with f just going from r to r. The approximation just tangent line. Right, so in this case, when f only has one variable, we get the value of f at x is approximately equal to the value of f at p, some point, some real number. Notice I put no hat here, plus f prime of p times x minus p. The only real difference is that we have to come up with the correct notion of multiplication in the vector set. Right? Okay. So for a second, let's suppose n is equal to 2. Which makes f of x hat, we can now just call f of x comma y our point P. We'll just give specific names to the coordinates A and B. Then what does our approximation look like? We get f of x comma y is approximately equal to f evaluated at a comma b plus the gradient of f evaluated at a comma b dot x minus a comma y minus b. Now let's take this one step further. Expression is equal to f of a comma b plus the partial derivative of f with respect to x evaluated at a comma b times x minus a plus the partial derivative with respect to y evaluated at a comma b times y minus b. What is this an equation of? Yeah, a plane, right? This is not too far off from the standard equation of a plane. Yeah. So this is to say the linear approximation of a function of two variables is a plane. Or perhaps the more general statement is that for a function of n variables, the linear approximation is an affine linear function of n variables. Right? An affine linear function of one variable is just a line. An affine linear function of two variables is a plane. Okay. Right. So, yeah, let me just make a note of that. The far right-hand side of the approximation is an affine linear function. I guess I've just been throwing that term around. We defined this in class. Somebody remind me, what is an affine linear function? That would be a linear function. The affine part means that we moved around by some constant. Yeah, right, exactly. And the constant here is the function value of f at the point A, B, or the function value of f at the point P hat or general. Yeah.
I was going to ask why it's half on linear. Look at the function at AB.
Then it would be linear. But I mean, a linear function is also an affine linear function, just where the constant you're adding happens to be 0. Yeah. Good. Okay, let's do an example of some linear approximation. So let's let f of x, y be equal to 4 plus x minus x squared minus y cubed. Find a linear approximation at the point 1 comma 1. And then I'll ask you to approximate the function value. F evaluated at 1.01 comma 1.05. Okay, so what information do we need in order to come up with a linear approximation in the first place? Yeah. Okay, so remember x and y here are the variables. So we're not going to assign them values. Yeah, so that's a good place to start though. What are the values of a and b in our problem? Yeah, they're just the 0.11 that we're going to evaluate the function at. So in other words, we need to evaluate f at 1 comma 1, which is 4 plus 1 minus 1 squared minus 1 cubed, which is equal to 3. Okay, what else do we need to know? Yeah. Yeah, I'll need to calculate the partial derivatives and then evaluate those partial derivatives at the point that I'm interested in. Yeah, good. Okay, so gradient of f x comma y to partial derivative at x, partial derivative at y. What's the partial derivative of our function f at x with respect to x, I should say? Yeah. Yeah, good. 1 minus 2x. And how about the partial derivative with respect to y? Yeah. Yeah, right. 4 is a constant. X is a constant with regard to y. X squared is also a constant with regard to y. So this is the only term we don't lose. We get negative 3 y squared. Good. Okay. So what is the gradient of f evaluated at the point 1 comma 1? Well, we just plug in ones everywhere we see an x or a y. 1 minus 2 times 1 squared. Oh, no, not squared. 2 times 1. Comma negative 3 1 squared. Or negative 1 comma negative 3. Now we have all the data we need to plug into our formula for the linear approximation, right? Okay. So value of f near at points near 1 comma 1 is given approximately by f evaluated at our point, which is just 3, plus the partial derivative of f evaluated at 1 comma 1. So this is actually a negative 1, right? The component first component of our gradient, times x minus 1 minus the partial derivative of f with respect to y evaluated at 1.1 comma 1 is -3. We calculated the second component here times y minus 1. Okay, that's it. That's our linear approximation. Now, what do we do in order to use this to approximate the function value at this point? 1.01 comma 1.05. Yeah. Yeah, we'll just plug in this into our linear approximation, the right-hand side. What is the advantage of doing this? Well, we're doing fewer computations, right? All we're doing is subtracting and then multiplying through. Whereas we have to do 1, 2, 3, 4, 5 multiplications here. And then 1, 2, 3 additions. So we're saving ourselves a little bit of computational time. All right. So f at 1.01 comma 1.05 is approximately equal to 3 minus 1.01 minus 1 minus 3 times 1.05 minus 1. And if you do the arithmetic here, what is it that you get? Yeah, 2.84. Good. So anytime we make an approximation, we would like to know how good of an approximation it is. Well, in a case where we're dealing with a fairly simple function like this, it's not so hard to actually just calculate the value of the function instead of just approximating it. We can tell how far off we are. So actual value is approximately 2.832275. Okay, so not an altogether terrible approximation. The last decimal place is off, even counting rounding, but we did very little computation to get it. So that's the value of linearization, is that we are able to, if we are close enough to the point we're centered at, we're able to come up with fairly reasonably good approximations of the function. Okay, so we'll also see the notation. L sub f and x hat centered at p to f evaluated at p plus gradient of f evaluated at p dot x hat minus p hat. L standing for linearization. So right, we say L sub f of x semicolon p is the linearization of f at point p. Okay. Right. So now we are in a position to give a general definition of what it means for a graph of a function of n variables to have a tangent set. Right? We define it using this notion of linearization. So f, a real value. Function. With domain. Subset. Of Rn. And differentiable. At P. Then the graph of the linearization of f at P is called the tangent set. Tangent set, sorry, to the graph of f at point p hat comma f of p hat. Okay, so where does the tangent set live? Get some clue from the fact that it has points that are of this form. Right? What dimension vector is P? Yeah, P is an n-dimensional vector. And now we're just considering one extra component, right? The value of f at this point P. That's a real number, right? Because f is a real value. So the points that form the tangent set are n+1 dimension. Right? They sit in a space that is n+1 dimension. This is consistent with what we were saying about the graph of a function with n variables lives in the space Rn+1. So think back to a curve again, right? Curve is given by a function of one variable. We draw its tangent line. It has one variable in it, but again, it takes us 2 dimensions to draw that. Right? So the tangent set lives in the same space as the graph of the function. This is consistent. Okay. So that is the tangent set is given as the set of points satisfying. Oh, sorry. Set of points. Which points? This set of points. Set comma v in Rn+1. Satisfying. V is equal to f of p hat plus the gradient of f evaluated at p dot x hat minus p hat. Okay. So let's look at another example, or perhaps you kind of already looked at this example, but let's take a slightly different perspective on it. I just forgot that. Thank you. Yeah, the gradient still takes an n vector as input. Thanks. Okay, so. Okay, so for example, the tangent plane of f, a real value function of two variables, at P, the set of points x, y, and z in R3, so that z is equal to f evaluated at a comma b plus partial derivative of f with respect to x evaluated at a comma b times x minus a plus the partial derivative of f with respect to y evaluated at a comma b times y minus b. Now, this you rearrange this the right way, this kind of looks like how we learned how to parameterize a plane using two non-zero parallel vectors. Okay, if you just do a little algebra here, you might be able to get into that form. The question is really what the vectors are that you're looking for. Give you a warning that I'm going to ask you in great detail to demonstrate this on the next quiz. Okay, so think about that. But for now, why don't we look at some other way to rearrange this equation of a plane. Okay. So, okay. So what do I want to say? Let's consider the cross section of the graph of f of x, y at x equals a. Okay. This gives a new function of the variable y. Okay, that is to say, I plug in the specific value a for x to the function f. I can essentially consider this a function of a single variable, right? Call it h of y. Yeah. Okay. Now, the tangent line of h at y equals b, just from calculus 1, right? Let me write the equation of this line. B is equal to h evaluated at b plus the derivative of h, right? And I specifically use the Roman d here because h is just a function of a single variable. So it's unambiguous what I mean by taking the derivative. Evaluated at b times y minus. Okay. Let me now go back on my substitution of h for f. Or another way to write this is that z is equal to f of a comma b plus partial derivative of f with respect to y evaluated at a comma b times y minus b. Okay, so all I've done here is used this declaration, this definition, right? H of b is just f of a comma b. Partial derivative of h with respect to y. I'm sorry, the derivative of h is the partial derivative of f with respect to y. Here, not only are we treating x like a constant, but we've actually substituted a constant in. Yeah. Okay, so we have some type of an equation for a line here. Which kind? Which type of equation is this for our given line? Yeah. Well, when I rewrite this, when I put my f back in here, this is now an equation of a plane, right? We also have another equation of a plane. What form of an equation for a line consists of two planes intersecting? So that's not exactly where we are, right? Yeah. We'll talk more about that tomorrow. But for now, yeah. It's not the vector form. Yeah. The symmetric form. Remember, the symmetric form of a line produces two equations of two planes that intersect in that line it's specifying. Right? So we started with the equation of the tangent plane of f at the point a comma b. And then by fixing a specific value of x, we have now produced the symmetric equation of a line. What is that line? It's the tangent line to the curve that lies on the graph when you intersect it with the plane x equals a. So this is somehow related to what you were talking about, right? You were looking at what happens when you cut the graph of a surface of a 2D function. I'm sorry, a function of two variables. You get a curve, right? So that is to say, when we choose a fixed value for x, we're slicing the graph of f of x, y at that value of x, and we're getting a curve out. What we've demonstrated here is that for any cross section on the graph, the tangent line at a point is contained in the tangent plane of that point when you look at the entire graph, not just the cross section. Let me say that again in reverse order of what I said that time. If you take the graph of a function of two variables and look at the tangent plane at a point, any cross section you take that contains that point will have a curve whose tangent line lies in the tangent plane. Okay. No, sorry. So let's record some of this. I've been talking a lot, not writing. So we have formula. Sorry, we have a symmetric equation. X equals A, comma, Z minus F of AB is equal to the partial derivative of F Y AB times Y minus B. Right, remember this is kind of the degenerate form of a symmetric equation where the coefficient on the normal vector for X is 0, so we can't divide by it. So we get 2 equations instead of a string of 3 equalities, right? Okay. These 2 planes intersect in the tangent line to the curve where X equal A intersects the graph of F of X. At point B. The broad overview of what I'm saying is that the tangent plane contains all the tangency data for any cross section that you can take, all the lower dimensional tangent structures. Okay, one thing students have found confusing in the past, just terminologically, we define the tangent set, right, in this definition. And then we still use this terminology of tangent plane as tangent line. Tangent lines and tangent planes are just specific examples of tangent sets. Right? A one-dimensional tangent set is a tangent line. A two-dimensional tangent set is a tangent plane. Sometimes you'll hear the terminology, a three-dimensional tangent set is just a tangent space. But after that, you just have to say tangent set of dimension 4, tangent set of dimension 5. There's no specific words for higher than 3 dimensions. Good. So here's a proposition that probably is something you glossed over in Calculus 1. But we'll see. Maybe you'll remember it. Proposition. If X hat is close to P hat, so that the magnitude of delta X hat, by which I mean the magnitude of X hat minus P hat, is close to 0, then the corresponding change in f, some function, which we'll call delta f, being f of x hat minus f of p hat, is approximated. by the following. The gradient of f evaluated at p dot the change in x. Okay, so what are we saying here? Think of this. This doesn't exactly make sense. What I'm going to write is not a valid formula, but if I could undo a dot product by division, this is what this form would take. What does this remind you of? Well, remember, the gradient is something that's kind of like the derivative, right? So in Calc 1, what is this saying? The difference of x divided by, I'm sorry, the difference of f divided by the difference of x is approximately equal to the derivative of f dx, right? If I have x close to some point p that I'm interested in, then taking the ratio of differences of x and p and the value of f at x and the value of f at p, this approximates the derivative, right? Of course, this doesn't make any sense, right? Because this is a scalar and I'm dividing it by a vector. What does that even mean? Nothing. This is the wrong thing. But structurally, equationally, it's the same spirit of what we're trying to say here. Okay. Yeah.
Why is it
Why is it at p? So well, okay. If it were at x, x is the point that we're moving around, right? X is supposed to be within some open set around p, right? So if we again think of the gradient as like the derivative, what we're saying is the instantaneous rate of change at p characterizes the growth of f at any point x near enough to p. That's why we take the gradient of f at p, because that's where we know the differential information, right? And as we let x change, the derivative at p still tells us approximately how much the function is changing. Is that okay? All right. This is called differential approximation. One quick example. So let's let h of x, y, z be equal to 2z times ln of e plus x times y. Given that h evaluated at this point 2, I'm sorry, 0, -2, 5. And what is this value? What is the value of the function here? So we get, plug it in, 0 for x and -2 for y. We get ln of e is 1, right? So yeah, total we get 10. Good. Okay. given this, use a differential approximation to estimate the change in H if delta XYZ is equal to the vector 0.01, 0.05, negative 0.2. Okay. So again, I'll ask, what do we need to calculate in order to apply this formula? Yeah, so we want to find the gradient of f and then evaluate it at this point. We know the function value at. Good. Okay, so first let's just compute the gradient of h. What is the partial derivative with respect to x of 2z ln e plus x times y? All right, so we've got our constant out front, right? 2z. That's fine. Yeah. Almost. So we get 2z, which was the constant, and then the derivative of ln of x plus, I'm sorry, the ln of e plus x times y is 1 over this, right? So e plus x times y times the derivative of just this bottom part. What is the derivative with respect to x here? Just y, right? E is a constant. Okay, so we get a y in the top here. Okay. So how about the derivative with respect to y? Well, it's almost exactly the same as this, but we get an x in the numerator instead, right? 2zx over e plus x times y. And how about the z partial derivative? Yeah, right. We only have the one z in here, and that differentiates to 1. Good. 2 ln e plus x y. Here's our gradient. Then our next step is to evaluate this gradient at the point. At this point, 0, negative 2, 5. Right. So h evaluated at 0, negative 2, 5. Well, I'll dispense with the arithmetic and just tell you the answer. Negative 20 divided by e, comma 0, comma 2. Yeah. Okay. And now my final step, all I have to do is calculate a dot product, right? To estimate the change in h. Okay. All this information together tells me that the change in our function h is approximately given by negative 20 divided by e 0, 2 dot 0.01, 0.05, negative 0.2. Okay. If I actually calculate this dot product, I get approximately negative 0.47358. Okay. So yeah, sometimes we're interested in just how much a function is changing without having much information about it. So this is useful for that. Okay, so I'll see you all tomorrow and have a good evening and rest of your day.